to take a look at multiple integration. You might want to revisit integration in general on the YouTube channel to get a little bit of a refresher on how integration works before you extend it into 3 variables. So we're going to be able to evaluate an iterated integral and be able to use that to give the area of a plane region. So what is an iterated integral? An iterated integral is going to be an integral that has a variable region and that iterates, so multiple pieces. So for instance, I typically don't write something like 0 to x, y dx because I'm going to have issues with the bounds and then integrating with respect to x when I've got a y in the problem. So if I wanted to work with this method, the integral from 1 to x, if I do that, I'm going to consider x to be constant. So it works not like an improper integral, it works like partial derivatives. So we're going to treat x like it's a constant when we actually integrate. So 2x squared is just going to stay out there, and I'm going to integrate y to the negative 2. So if I integrate y to the negative 2, I add 1 to it, which is y to the negative 1. That's where that comes from. The integral of 2y would be y squared, and then we would treat it just like the fundamental theorem of calculus says, and plug in the x minus plug in the 1. And then we get an equation of 1 variable. So this works just like partial derivatives, where you're holding one of those variables as a constant. Now we start to get into the iterated pieces. I can integrate an integral, which I know take a moment to process that. It becomes a little crazy. So if I wanted to do the same thing, but I'm going to take a double integral, we work from the inside out. So I'm going to take the integral that I calculated already on the previous slide, and then I'm going to integrate that to get x cubed minus x squared minus x. Then I'll apply the fundamental theorem of calculus. So we wind up at a numerical answer because we went from a function of 2 variables to 1 variable because we treated a variable as a constant. And then we applied the fundamental theorem to get the number. So integrals like this are called iterated integrals. We typically use brackets like we're seeing in the previous example, but not always. So sometimes it can just have 2 integrals in front of it. The inside limits can have a variable in them because that's telling me what to hold as a constant. But the outside limits must be constants with respect to both variables of integration. So for instance, in example 2, the outside limits indicate that x is going to be between 1 and 2. So when we go back to that example, I'm saying my x values are between 1 and 2. And then as I progress, I look at the inside limits, and they tell me that y is between 1 and x. So that's why I have 1 here on the horizontal, and then I have, I'm not sure what this actual x value is here. And I have the line y equals x. So together, they describe the region of integration R using the iterated integral. And to build on that, we can find the area of a plane region. So we just looked at 2-dimensional regions. Now we're going to look at a plane region. There's a couple of rules for this. So when I'm dealing with plane regions, I have to consider the limits of integration for x and the limits of integration for y, and I have to treat them differently depending on which situation I have. The thing that's going to remain the same is that I am going to still be using the fundamental theorem of calculus. So specifically, if I want to consider that x is fixed, but let y change, then I could write it like this. If I want to combine that to get my iterated integral so I don't have these g's hanging out in my brackets, I can write it as a to b are constants, and then I have g1 of x to g2 of x, which would be one of those I'd be holding constant, the other one would actually be a bound. So if I'm imagining this in multiple dimensions, If the area is vertically simple, meaning, see that little vertical rectangle there? So it's a vertical relationship. Then I'm going to do this with the limits of integration that are going to be from x values, from a to b. If it is horizontally, so like think about the sideways parabola, x equals y squared. So if it's a horizontal, then I'm going to consider my y limits, c to d, and that means that dy is going to be on the outside. So here, dx is on the outside. Here, dy is on the outside. That has to do with the orientation being vertical or horizontal. So, what does this actually look like in practice? So, the area of a region in the plane, this is a summary slide. If we have something vertical, you would use the top one. Horizontal, you would use the bottom one. So, let's look at an actual problem. In this situation, I have a vertical region. So, this is pretty much vertical looking like it is here. If that's the case, dx goes on the outside, and I'm going to integrate from a to b after I evaluate the integral of dy, which is y, from c to d. Now, if I want to go from c to d, I could do that as d minus c, because, you know, the integral runs f of b minus f of a. So that's where d minus c comes from, is by taking the integral of dy, which is y, and then I'm going to plug in d minus plug in c. But I still have the integral from a to b out front. So now I'm going to integrate with respect to x. So if I integrate d minus c, that would be d minus cx, because we know that d and c are constants. So the integral of any constant is the constant times x, which I am then going to evaluate from a to b. So I have my d minus c and then times my b minus a. This is a bit tricky and proof-like, so I'm going to post some help from Khan Academy here as well. But you should be able to kind of understand the gist of the formulation here from this lecture.